In section 1.3, new functions from old functions, we start with the basic functions we discussed in section 1.2 and obtain new functions by shifting, stretching, and reflecting their graphs. We also show how to combine pairs of functions by the standard arithmetic operations and by composition. And by applying certain transformations to the graph of a given function, we can obtain the graphs of certain related functions. This will give us the ability to sketch the graphs of many functions quickly by hand. It will also enable us to write equations for given graphs. So we're going to consider the translations. So take a look at the translations that we have here. We have vertical and horizontal shifts. Now if you notice, in the center here, this is our function y equals f of x. Now if you take a look at the first one, y equals f of x plus c, shift the graph of that function c units upward. So therefore it would shift up c units. When you have y equals f of x minus c, then you will see that the distance that it shifts is c units downward. And then if you have f of x minus c, then you will be shifting it c units to the right. And if it's y equals f of x plus c, then you will shift the graph of the function c units to the left. Okay, now let's consider the stretching and reflecting transformations. So if c is greater than 1, to obtain the graph of the function would be the following. So again, if you take a look at the middle here, this is the function y equals f of x. So if you multiply it by a factor of c, then you will stretch the graph of that function vertically by a factor of c. If you multiply the function by 1 over c, then you would shrink the graph of the function vertically by a factor of c. And if you take the value of the function and multiply its input by the value of c, then you will shrink the graph horizontally by a factor of c. And if you would multiply the input by 1 over c, then you would stretch the graph horizontally by a factor of c. If you multiply the entire function by a negative, then you would reflect the graph of the function about the y-axis. If you multiply the input of the function, then you would multiply the input by a negative number, then you would reflect the graph of the function about the y-axis. Okay, now in this figure, it illustrates these stretching transformations when you apply them to the cosine function, when you take the value of c and it's equal to 2. So for instance, in order to get the graph of y equals 2 times the cosine of x, we would multiply the y-coordinate of each point on the graph of y equals the cosine of x by 2. And what this means is that the graph of the function y equals cosine of x would then get stretched vertically by a factor of 2. Now let's take a look at example number 1. Okay, what we're doing is we're transforming the root function. And the root function is the first function that you can see on the left, y equals the square root of x. And we're going to use transformations to graph the following. Y equals the square root of x minus 2. If you look at the second graph, that means that we shifted the graph 2 units down because c would be represented by negative 2. Now if you take a look at the next graph, y equals the square root of x minus 2, the value of x is being subtracted by 2. So therefore you're shifting it horizontally to the right 2 units. In the next graph, we have y is equal to the negative times the function square root of x. And what you would do is you would reflect the graph of that function about the x-axis. The next function, you have y is equal to 2 times the square root of x. And what you've done is you've stretched the graph of that vertically by a factor of 2. And the last one, you have y is equal to the square root of negative x. And x being the input is now negative, so therefore it's reflecting the graph about the y-axis. Okay, now in example number 2, we want to be able to sketch the graph of this following function. Okay, now in order to sketch the graph of the function, the best way to do this is probably to complete the square. So if you want to take a quick review of how to complete the square, right, so we know that we have the function x squared plus 6x, and what we would do is we would subtract 10 to both sides. And then by completing the square, we would add c to both sides. Okay, and then c is going to equal 1/2 of the value of b, and then squaring it. So therefore, c would then equal 1/2 of 6, and 1/2 of 6 is 3. And when we square that, we would get the value of 9. So now we would have x squared plus 6x plus 9, which is equal to negative 10 plus 9. So now when we factor, we would end up with x plus 3 squared, which is equal to negative 1. Setting this equal to 0, the function would then be x plus 3 squared minus 1. So therefore, plus 1. Therefore, f of x is going to equal the function x plus 3 squared plus 1. So from here, you can determine what the vertex is. And the vertex is negative 3, 1. So you can see there you're plotting it. And then you can find other table of values. Okay? But what happened here is that this means that we obtained the graph by starting with the parabola of y equals x squared. And what we've done is we've shifted it to the left 3 units. So this is telling us to shift the graph 3 units left. And then the plus 1 tells us to shift 1 unit upward. And again, rather than actually making table of values, you can just use transformations to be able to answer that question. All right, let's take a look at the next example, example number 3. So we want to sketch the graphs of the following functions. So we have y equals the sine of 2x. Now, we obtain the graph of y equals the sine of 2x by first graphing y equals the sine of x, which is here in figure 6. Now, what we're going to be doing is because we're taking the value of x and multiplying it by 2, then that means we're going to be compressing horizontally by a factor of 2. Thus, whereas the period of y equals the sine of 2x is 2 pi, then the period of y equals the sine of 2x is 2 pi over 2, which would be pi. So again, let me write that out here. So the period for this function, y is equal to sine of x, is 2 pi. And then over here, the period is y equals, again, the sine of 2x because that's the function. And so the period would then be 2 pi divided by 2, which is equal to pi. Now, if we take a look at the next graph, we have y is equal to 1 minus the sine of x. So again, we're going to start with the graph y is equal to the sine of x as we have in figure 6. Now we're going to reflect about the x-axis to get the graph of y equals the negative sine of x. So because this is y is equal to negative sine of x, then again we reflect about the x-axis. And that's according to the rules that we have in the previous slide. And then what we're going to do is, because you have a value of 1, then you're going to shift 1 unit upward to then get the following graph. Okay, now for example number 4, okay, we are modeling amount of daylight as a function of time of year. So in this figure, it shows graphs of the number of hours of daylight as functions of the time of the year at several latitudes. So given that Philadelphia is located at approximately 40 degrees north latitude, we want to find a function that models the length of daylight at Philadelphia. Now, if you notice that each curve resembles a shifted and stretched sine function, by looking at the blue curve, we see that at the latitude of Philadelphia, daylight lasts about 14.8 hours on June 21st and 9.2 hours on December 21st. So the amplitude of the curve, meaning the factor by which we have to stretch the sine curve vertically, is the following. So again, on June 21st, let me go ahead and write that here. Oops. So on June 21st, we know that daylight lasts about 14.8 hours. And then from September, December 21st, it is 9.2 hours. Okay? So the amplitude of the curve again is the factor by which we have to stretch the sine curve vertically, is taking the value of 1/2 and then multiplying it by 14.8 minus 9.2, which gives you a value of 2.8. Now, by what factor do we need to stretch the sine curve horizontally if we measure the time t in days? So because there are 365 days in a year, the period of our model should be 365. But the period of y is equal to sine t is 2 pi. Because if you recall, the period of the sine curve is 2 pi. So what we would do is, in order to find the horizontal stretching factor, what we would need to do is take the value of c, which would be the horizontal factor, and that would be 2 pi divided by 365. Now we also notice that the curve begins its cycle on March 21st. So on March 21st, that would be the 80th day of the year. And since it's the 80th day of the year, then that means that we have to shift the curve 80 units to the right. Okay, also, we would have to shift it 12 units forward. So therefore, we would get the following model. We would say that the function L of t is equal to shifting it 12 units, so it would be 12 plus again, coming back up here, we know that we have 2.8 as the what? 2.8 is the amount that we're stretching the curve vertically by. So we have 2.8 times 2 pi over 365, and we're shifting it 80 units to the right, so that would be t minus 80. Okay, next, we want to be able to sketch the graph of the function of the absolute value of a function. So the first thing we want to do is we want to graph, and if you look in figure A, y equals x squared minus 1. So we have the function x squared, and we shifted it down 1 unit. Now we see that the graph lies below the x-axis, and it's below the x-axis here in yellow between -1 and 1, but not inclusive. So what you see here is that we would then reflect the part of the graph here about the x-axis to then obtain the graph of y is equal to the absolute value of x squared minus 1. Now here you can see that between -1 and 1, the value is negative. But since we're dealing with the absolute value, therefore, this curve now is above the x-axis because it now is positive due to the absolute value function. Okay, now we also have combinations of functions. So two functions f and g can be combined to form new functions f plus g, f minus g, f times g, and f divided by g. So in a manner similar to the way we add, subtract, multiply, and divide real numbers, the sum and the difference functions are defined by the following. So it's important to write the definition. F plus g of x is equal to f of x plus g of x. F minus g of x is equal to f of x minus g of x. And also, we want to make note that if the domain of f is a and the domain of g is b, then the domain of adding those two functions together is the intersection of a and b, because both f of x and g of x have to be defined. So for example, the domain of f of x, which is equal to the square root of x, is including 0 to infinity, and the domain of g of x, which is equal to the square root of 2 minus x, would be -infinity to 2 inclusive. So the domain, when you add those two functions together, would be the intersection. So where do those two intervals intersect? Well, they intersect between the values of 0 to 2 inclusive. And similarly, the product and quotient functions are defined by the following. So if you take a look at that, you can see that f of times g of x is equal to both functions being multiplied together, and f divided by g of x is the two functions dividing where g of x cannot equal 0. Now, the domain of f of g is a intersection b, but we need to take into consideration that we can't divide by 0. And so the domain of f divided by g is all real numbers that are intersect between the sets of a and b, whereas g of x cannot equal 0. So for instance, if we had the functions x squared and x minus 1, then the domain of the rational function x squared divided by x minus 1 would be the set x such that x cannot equal 1, or the interval notation -infinity to 1, union 1 to infinity. Now, there is another way of combining two functions to obtain a new function. For example, we can use u substitution. So suppose that y is equal to f of u, which is equal to the square root of u, and then we would let u equal g of x, which would equal the function x squared plus 1. So since y is a function of u, and u is in turn a function of x, then it follows that y is ultimately a function of x. We would compute this by substituting the following. Y is equal to f of u, which is equal to f of g of x, and therefore the input is x squared plus 1, and that would give you the entire function square root of x squared plus 1. And this procedure is called composition because the new function is composed of the two given functions f and g. So in general, given any two functions f and g, we start with a number x in a domain of g and find its image g of x. If this number g of x is in a domain of f, then we calculate the value of f g of x. The result is a new function obtained by substituting g into f. And again, it is called the composite function. So here's a definition. Given two functions f and g, the composition function is called the composition of f and g, defined by the following. F composite g equals f g of x. So the domain of f composite g is a set of all x in a domain of g, and that g of x is in a domain of f. So in other words, we defined whenever we see both functions, you want to consider them as machines. So the input x is the input of g, which then becomes g of x, which then gives you f of g of x, and you can see what the composite function does to you in the form of a machine. Now, in example number 6, let's go ahead and then apply the composition functions. So for the first one, we want to be able to find f composite g. Okay, now my suggestion is to always write down what the definition is. So the definition is f composite g of x would then be the following: f of g of x. So you would substitute g of x to be x minus 3. And now that becomes the input on the function of f. And so therefore we would end up with x minus 3 squared. And similarly, we want to find the composite function of g composite f of x. And so again, writing down the definition, this becomes g of f of x, where f of x is now the input on the function g. And since we know that f of x is x squared, then we would now substitute the value of x squared into x into the function g of x. So we would get x squared minus 3. Now let's take a look at example number 7. Okay, so we have our two functions. We want to find each function and its domain. So for part A, again, we're going to write down the definition. So we have f composite g of x. And again, the definition is f with the input g of x. And so the input is the function the square root of 2 minus x, and we would plug it into the function f of x. So we would get the square root of the square root of 2 minus x. Okay, now in other words, we can rewrite this using fractional notation. So what you're seeing here is you have the inside function is the square root of 2 minus x, which is the same thing as 2 minus x to the 1/2. Okay, and then using the second root, then that means you have on the inside 2 minus x to the 1/2, and that's raised to another fractional exponent to the 1/2. And therefore, you would end up with 2 minus x to the 1/4 when you multiply those exponents together, which would then be the fourth root of 2 minus x. Now, what we would say now is that the domain of this function would be such that x such that 2 minus x is greater than or equal to 0, which would then mean that x such that x would have to be less than or equal to 2, which is also an interval notation from negative infinity to 2 with a bracket. Okay, if we take a look at part B, you want to find G composite F. And again, writing down the definition, we have G where the input is f of x. And so we would have G of the square root of x which would then equal the square root of 2 minus the square root of x. Now in this case, for square root of x to be defined, we must have x to be greater than or equal to 0. So to be defined, we must have 2 minus the square root of x be greater than or equal to 0. So in order to find the domain of this function, then we could see that 2 minus the square root of x on the inside of this radical has to be either greater than or equal to 0. Now, if we wanted to solve for the square root of x, we would add 2 to both sides, divide by 2, and then flip the inequality. So we would have the square root of x, which is now less than or equal to 2. And if we square both sides, then x would be less than or equal to 4. And so therefore, we would say that the domain would be x such that x is in between 0 and 4, which is also equal to the interval notation 0 to 4. And now if we take a look at C, we want to find f composite f of x. And again, writing down the definition, f of x. So the input is the square root of x, and that is the input of the function square root of x. And if you recall from the first part in part A, this would then become the fourth root of x. So the domain of this function would be x such that x is greater than or equal to 0, or in interval notation, we would have 0 to infinity. Now in part D, we have G composite g of x, which again is a definition g of x, which is equal to g, and then the input is the square root of 2 minus x, which then becomes the square root of 2 minus the square root of 2 minus x. So we need to find an expression and define it when it's both. So because you're looking at this function, the first radical inside the radical is 2 minus x, and we want to find out when that's greater than or equal to 0. And we also have what's entirely under the radical is 2 minus the square root of 2 minus x. And that also has to be greater than or equal to 0. So the first inequality, if we solve for x, subtract 2 to both sides, and divide by a negative, then we would flip the inequality to get x is less than 2. And then in the second one, what we would do is we would first subtract 2 to both sides, so we get negative square root of 2 minus x, which is greater than or equal to 0. Okay. And then, sorry, not 0. That's negative 2. And if we divide by a negative, then again we would flip the inequality, so we would have the square root of 2 minus x, which is less than or equal to 2. And if we square both sides, we would have 2 minus x, which is less than or equal to 4. And therefore, solving for x would mean that we would need to then subtract 2 to both sides, divide by the negative. So again, we're going to flip the inequality. And so then x would be greater than or equal to 2. So what that means here is that you have x is less than 2, and you have x is greater than 2. I'm sorry, when we divide that by negative, we should get it x is greater than or equal to negative 2. So from here, we would have the domain of the following. And the best way to write this in set builder notation is write x in the middle, and then use your inequality statements. So x is in the middle. We would say x such that, well, if it's greater than negative 2, that means that x has to be greater than or equal to negative 2, meaning that the arrow is pointing to the smaller number. And then again, x is going to be less than or equal to 2, so therefore it's going to be less than or equal to 2. So that would be your set builder notation. And then interval notation would be bracket negative 2 and then 2 with your bracket. Okay, now if we wanted to be able to then start with example number 8 and find f composite g composite h. So then we would again write the definition. So f composite g composite H. And so that definition would then be f of g of h of x. So that means we would have f of g in the function h of x is x plus 3. So that is the input for the first one. And since that becomes the input on the function g, then that would be f of x plus 3 to the 10th power. And then now that becomes the input on f. So now you're going to replace all the x values with x plus 3 to the 10th. So in the numerator, we would have x plus 3 to the 10th all over x plus 3 to the 10th power plus 1. Okay, and then we can also decompose a function. So if we want to decompose a function, if we're given a function f of x, capital F of x, which is equal to the cosine squared of x plus 9, we want to find what were the functions f, g, and h. Okay, so since f of x is equal to, since we see that this function f of x is equal to the cosine squared of x plus 9, okay, so let's go in terms of in a different order. So we would know that we would start at the beginning, which is on the inside of the function. So the inside of the function, in this case here, meaning what's inside the parentheses, would represent the value of h, or the function of h. So this would be h of x, which is equal to x plus 9. That would be the first input. And then the second input would have to be g of x. So g of x would then represent the function cosine of x. And then we could say that f of x would then have to square the entire function. So you have to kind of work backwards here. So if we look at this, like we did in a previous example, and find the composite of all three of these functions, and again using the definition, so again, we would see that h of x represents the first input, which is x plus 9. And then again, g of x represents cosine of x. So now this becomes the cosine, and then x is now going to be replaced with x plus 9. And then f of x means that we need to take the value of the input and then square it, which is the reason why that when you square this entire function, then it becomes cosine of x plus 9, and we would square that, which would then give you cosine squared x plus 9.